What aspects of 5G that you have learned about so far has made the deepest impression on you? I guess most of you will think of 5G's three application scenarios: eMBB, URLLC, and MMTC. The ITU's visions for 5G use in these three scenarios include a peak rate of 10 gigabits per second, end-to-end latency of 1 millisecond, and a connection density of 1 million connections per square kilometer. To achieve these goals, 5G networks, especially 5G wireless networks, need some new key technologies. Some of these technologies increase the 5G peak rate, others reduce latency, and others yet increase the number of connections possible at one time. We also need to consider that 5G uses high-frequency bandwidth, so its coverage is limited. As such, we will need new technologies to enhance 5G coverage. Only in this way can 5G networks meet the targets set by the ITU. In the currently frozen Release 15 version, no standard MMTC scenarios have been defined. This means that the key technologies that will be used to increase the number of system connections have not been frozen. Therefore, we will focus on the three types of key technologies that have been frozen. These include technologies to increase coverage, technologies to improve rates, and technologies to reduce latency. As you might know, according to the Shannon's formula, C equals B by log 2, 1 plus Sn, increasing bandwidth B is the most direct way to boost the user rate. This is like widening roads to increase the vehicle flow rate. 5G requires a large number of spectrum resources of hundreds of megahertz or even 1 gigahertz. Considering that various existing wireless communication systems currently occupy many spectrum resources, 5G will need to use high-frequency bands for communication in the future. However, high-band communication has two major disadvantages when compared with lower-band communication. The first disadvantage is that there is more path loss. There is less signal diffraction, so the signals have a harder time getting around obstacles, as shown in the figure. Given the same transmission distance, the propagation path loss for high-band signals is much greater than that for low-band signals. This means that the coverage radius of a cell operating on the high-frequency band is substantially smaller than the coverage radius of a cell working on a lower frequency band. The second disadvantage is that the high-band communication provides unbalanced uplink and downlink coverage. The higher the frequency band, the greater the imbalance between the uplink and downlink coverage. The uplink coverage is worse than that in the downlink. As shown by the figure, the transmit power of a base station is much greater than that of a mobile phone. As a result, the coverage of the uplink traffic channel is much smaller than that of a downlink traffic channel. Signals transmitted from a mobile phone at a cell edge may not be able to reach the base station. To address these two disadvantages, Huawei proposes the uplink and downlink decoupling solution, which has been written into the 3GPP specifications as a standard technology. Usually in mobile networks based on time division duplex, or TDD, uplink and downlink data are transmitted on the same frequency. That is, the uplink and downlink data are coupled. In the 5G decoupling technology that Huawei introduced, 5G new radio base stations, otherwise known as G-Node B, use high frequencies for download communications and sometimes low LTE frequencies for uplink communications. The uplink frequency band depends on how close UE is to the base station. When the UE is close to the base station, there's no need for decoupling, and both uplink and downlink signals are carried on the high frequency band. When the UE is far from the base station, the signals are decoupled, with the downlink signals carried on the high frequency band, while the uplink signals are temporarily carried on a low LTE frequency band. In this way, improving uplink coverage. Next, let's learn about another type of key technologies. Technologies used to improve data rates. 5G provides a much higher data rate than 4G. This is largely due to new technologies like new channel coding technology and massive MIMO. First, let's look at the new channel coding technology. What is channel coding? Simply speaking, to overcome the problem of poor radio channel reliability, in addition to the original useful information bits, a certain proportion of redundant bits are added. This can protect useful information bits and improve the reliability of information transmission. Imagine you bought a porcelain vase on the internet. To prevent the porcelain from being damaged during delivery, a lot of additional foam packaging is added. The channel coding process is a bit like this. According to the latest Frozen Protocol 3GPP Release 15, in a 5G eMBB scenario, the control channels use polar codes, but the traffic channels use a low-density parity check, or LDPC for short. The two coding technologies have many advantages over the 4G turbo coding technology, as shown in this figure. LDPC offers better decoding performance, less decoding latency, and more power efficiency. Also, polar technology results in a lower error rate in data transmission when compared with turbo technology under the same signal-to-noise ratio. LDPC and polar coding have high coding efficiency. Continuing the porcelain vase and foam packaging example from before, you can protect your vase better by just adding more packaging. But the packaging gets bigger too. This is what we mean by efficiency: more protection from the same amount of packaging. LPDC and polar add just enough redundancy to 5G communications to guarantee that data is transmitted and received reliably. This raises the efficiency of information delivery and, in so doing, raising the peak throughput for end users. Now, let's take a look at another technology used to improve data rates: Massive MIMO. What is Massive MIMO? This term literally means a large-scale antenna array with at least 16 antennas. Huawei achieved an industry first by developing the Massive MIMO with 64 antennas to achieve 64T64R. With more antennas, more flexible and precise 3D narrow beamforming can be realized, so that more users can multiplex wireless time frequency resources. In this way, the large-scale antenna array solution improves coverage capability and system capacity, while reducing system interference. It is similar to the wireless routers we use at home. You may have noticed that newer wireless routers have more antennas, and these new multi-antenna routers provide better signals and faster rates. So what are the advantages of Massive MIMO? Compared with 8T 8R antennas in 4G TDD system, Massive MIMO has more data streams. Generally, 8T 8R antennas can only transmit 2 downlink data streams, while 64T 64R Massive MIMO with narrower beams can provide 16 data streams in the downlink through space division multiplexing, or SDM. This means that base stations can allocate the same time frequency resources to 16 different users at the same time, greatly improving the overall cell capacity and reducing the interference among users in the cell. This makes base stations with 64T64R perfect for high traffic areas such as universities and central business districts. Then does the single UE rate increase? Yes. Compared with the 4G UE configured with 2 antennas, 1T, 2R, by default, the 5G UE is configured with 4 antennas by default to achieve 2T, 4R. The downlink peak rate of 5G UEs will dramatically increase with the downlink multiple layers of Massive MIMO. In addition, Massive MIMO beams can provide 3D coverage with horizontal and vertical beams, which greatly improve signal coverage of high-rise residential communities and hotels. Traditional 8R antennas, in contrast, only support horizontal beamforming. After beamforming, signals can only be sent along the horizontal plane, but cannot be sent along the vertical plane. Therefore, high-rise residential communities or hotels may have weak or even no signal coverage. Massive MIMO can make a difference. As stated earlier, Massive MIMO antennas make use of horizontal and vertical scanning, allowing 3D signal coverage. In this way, signal coverage is greatly improved for high-rise buildings. The rate of users in high-rise buildings can be effectively increased. Now, let's move on to the third type of new technologies that reduce latency. We know that one application scenario of 5G is URLLC, ultra-reliable and low-latency communications. Under ideal conditions, the end-to-end latency can be as low as 1 millisecond. This is far lower than the 4G standard 10 milliseconds. How is 5G able to deliver such low latency? Once again, we have a large number of new technologies to thank. Technologies like grant-free scheduling, D2D, and MEC. First, let's explore grant-free scheduling. Normally, when your cell phone transmits data to the base station, the mobile phone first needs to send a scheduling request. The base station then sends a scheduling grant to the phone, and then only after the phone has received the grant can it start transmitting the data to the new base station. With grant-free scheduling, when a phone needs to transmit data to the base station, it does not need to send a scheduling request. Instead, it can just transmit the data directly to the base station using a pre-reserved resource block. Comparing the two processes illustrated here, it becomes clear why grant-free scheduling has less latency. There is no time spent on the request and authorization processes. This technology is expected to be frozen in Release 16. It will be mainly used for latency-sensitive URLLC scenarios. D2D is another technology that reduces latency. What is D2D? D2D means device-to-device communications. That is, a device directly communicates with another device. Common D2D applications include Bluetooth in mobile phones, Wi-Fi Direct, and walkie-talkies. However, D2D technology is applied in 5G networks when a base station allocates spectrum to transmit user-plane data from direct communication among terminals. D2D has the following advantages. 1. Long transmission distance. Compared with Bluetooth and walkie-talkies, the D2D technology can cover a longer transmission distance of more than 1 kilometer. 2. Low transmission latency. D2D transmissions do not need to be relayed by a base station. Two mobile phones can communicate directly with each other. This means the transmission distance is shorter, which in turn means that there is less transmission latency. 3. High spectral efficiency. A D2D terminal reuses the spectrum resources of the cell, so the spectral efficiency of the cell is improved. So, now you can see how D2D technology can reduce latency. This technology is expected to be frozen in 3GPP Release 16. Let's now look at Mobile Edge Computing, or MEC, another technology that reduces latency. Latency is a concept that relates to device-to-device communication. The total latency of a service includes air transmission latency, terrestrial transmission latency, and device processing latency. Terrestrial transmission latency is the most significant contributor to latency among the three sources outlined above. How can it be reduced? The first idea is to shorten the transmission distance on the ground. As long as the distance is shortened, the transmission latency becomes smaller. How do we shorten the transmission distance on the ground? In the traditional 4G network architecture in China, base stations are located in lower-level city, while core network gateway devices are deployed in central city. The distance between the two often reaches hundreds of kilometers, resulting in high transmission latency. 5G network architecture is different. For 5G networks, hierarchical core networks consist of Edge Data Center, or DC, Regional DC, and Core DC. They are deployed at different locations. Edge DC can be set up in lower-level cities. Regional DC can be set in the central city of the region, and the Core DC can be deployed in the central city of the entire network as required. For low-latency services such as Vehicle-to-Everything, V2X, and Internet of Vehicle, or IoV services, core network gateways and IoV service servers can be deployed on an Edge DC. The Edge DC would only be a few kilometers to a dozen kilometers away from the base station. This would greatly shorten the distance of data transmission between the mobile network and the service users. In this way, lowering latency. In addition, the service server deployed at the edge of the mobile network can offload traffic data locally, greatly reducing the bandwidth requirements for the transport network and the core network. As shown in the figure, in 5G, about 35% Internet of Vehicle data would be offloaded at the edge DC. About 35% augmented reality, AR or virtual reality, VR data would be offloaded at the regional DC. And only a small amount of Internet of Things data would need to be transmitted to the core DC for offloading. This lesson has described the key technologies used on the 5G air interfaces. Uplink and download decoupling enhances 5G uplink coverage. New channel coding technologies along with massive MIMO increase the peak data rates, and 5G network latency is reduced by using grant-free scheduling, D2D and MEC. In the next lesson, we will learn about 5G's new architecture.